Hi everybody, in this video we're going to talk about what happens when we multiply the components of a vector by a scalar, which is just a number. And then we're going to use that knowledge to figure out how we can take a vector and find the components of a unit vector, which is a vector of length 1 moving in the same direction. Okay, but first we're just going to talk about what happens when we multiply the components by a scalar. So let vector v be some vector, and we'll say the components of vector v are x and y. So x would be the horizontal component, and horizontal meaning like this, and y would be the vertical component. The magnitude of the vector is denoted like this. Okay, so when we write v with two lines around it, that means we're talking about the magnitude of the vector, how long it is. Now, if we multiply both components, remember x and y would be the components of the vector. If we multiply both components by a, where a is just some scalar, it's just some other number, then we could ask ourselves, okay, what would the magnitude of the new vector be? Well, if we do that, then the magnitude of the resulting vector, which we can write this way, would be the absolute value of a times the original magnitude. Okay? So over here, we see these two lines, and then we see ax and then ay. So this just means that now we're talking about the magnitude of the vector that we get after x has been multiplied by the number a and y has been multiplied by the number a. Okay, so the magnitude of that resulting vector would just be the magnitude of the original vector times the absolute value of whatever number we multiplied the components by, okay, which we're calling a here. So this might make a little bit more sense after going through an example, so let's do that right now. Let's say we have a vector over here, and I'm just calling this vector f, maybe for Friedman. Okay, so I'm putting myself in there, which I get to do because I'm making the video. All right, so we have vector f over here. The components of the vector components would be negative 3i and 4j, let's say. Okay, so this horizontal vector is moving to the left by 3 units, and this vertical vector is pointing up, and it is 4 units long. Okay, so we can write that in a couple of different ways. We can say that vector f is equal to negative 3i plus 4j, or we can simply use the angle bracket notation and say that vector f is negative 3, 4. Okay, so we know what the components are. Now let's ask ourselves, what is the magnitude of vector f? How long is vector f? Well, to do that, to find the magnitude, notice that I have the two lines over here now, of vector f, we would take the square root of the sum of the squares of each of the components. So underneath the radical over here, we have negative 3 squared plus 4 squared. Okay, so what is that? So negative 3 squared is 9, 4 squared is 16, and then 9 plus 16 is 25, and the square root of 25 is 5. Okay, so the magnitude of angle F is 5. Okay, it's 5 units long. That's the length of it. Okay, so hopefully so far so good. Now let's go ahead and multiply both of these components by some number. And I chose the number negative 2 just for this example. And here we would get another vector. Let me scroll down a little bit so you can see that. So if we multiply both of these numbers by negative 2, then what would we get? Well, negative 3 times negative 2 is positive 6. So you can see that now we have this horizontal vector component of 6i, positive 6i, and 4 times negative 2 would be negative 8. So now you can see that instead of the vertical component being 4j, now it's negative 8j. Notice that this vector is moving down now. So in fact, both of these component vectors have switched directions because we multiplied by a negative number. This was moving to the left, this one is moving to the right, this one was moving up, this one is moving down, and they're also twice as long as they used to be. This one was 3 units long, now this one is 6 units long. This one was 4 units long, this one is 8 units long. Okay, so when we multiply the components by negative 2, as in this example, then the directions would switch and they would become twice as long. Okay, so now we can ask ourselves, what is the magnitude of this vector over here whose components are negative 2 times the components of vector f? All right, so to figure that out, we would do the square root of 6 squared plus negative 8 squared. Now, 6 squared is 36, negative 8 squared is 64, 36 plus 64 is 100, and the square root of 100 is 10. So that means that this vector over here has a magnitude of 10. Okay, and recall that this vector over here had a magnitude of 5. So when we took this vector and we multiplied the components by negative 2, the magnitude of the resulting vector became twice as large. Okay, the vector itself became twice as long. All right, let's go ahead and sort of recap what we just did. So we had the original components negative 3 and 4. We multiplied both of those components by negative 2. Okay, so I want you to compare what I wrote over here to what was written over here. So in this example, our x was negative 3, our y was 4, our a was negative 2. Okay? So negative 3 times negative 2 times negative 3 is positive 6. Negative 2 times positive 4 is negative 8. So when we found the magnitude of the vector that had components 6, negative 8, we found that that magnitude was equal to 10. Okay, so this is just sort of a recap of what we just did. But now I want to erase this part of it for a moment, just to make it more clear what this rule is saying. So again, our a is negative 2, our x is negative 3, and our y is 4. So this rule is saying that if we multiply these components by negative 2, then the magnitude of the resulting vector should be equal to the absolute value of a, which in our case was negative 2, times the magnitude of the original vector. Our original vector was vector f, and the magnitude of vector f was 5. We found that earlier. So if we multiply this by 5, what do we get? Well, the absolute value of negative 2 is positive 2, and positive 2 times 5 is 10. Okay, and we know that that is correct because we did the math over here and we found that the magnitude of the vector that has these components is in fact equal to 10. So this rule seems to work. Okay, it worked in this example, and it would work in any example. All right, now what should we call this vector over here? We know what the components are, and we know what we did to get it, but what should we call it? since we multiplied both of the components of vector f by -2, would it be correct to say that this vector is -2f? Is that correct? All right, so think about it on your own for a second. All right, now to answer that question, let's think of what it means to say that something is -2f. That means we start with some vector f, and then we make it go in the opposite direction because we're multiplying it by a negative number, and we also make it twice as long. Is this vector moving in the opposite direction as this vector? Actually, yes, it is. It is moving in exactly the opposite direction. If you forget about the heads for a second and just think about the slope of these lines, the slope of this line would be 4 divided by -3. Remember rise divided by run? So the slope would be 4 divided by -3, which is -1.3 repeating. The slope of this line would be -8 divided by +6, which is also -1.3 repeating. So the slopes are exactly the same, but this one is pointed this way and this one is pointed this way, which means that the direction has been flipped 180 degrees. Okay, it's moving in exactly the opposite direction. Okay, so that takes care of the negative. Is the length of this vector twice as long as the length of this vector? It is. We just said that, right? The magnitude of this vector is 10. The magnitude of this vector is 5. So this one is twice as long as this one. So we are justified in calling this vector -2f. Okay, so that's another important point, which is that if we have some vector, again, we'll just call the components of the vector x and y, then if we multiply both of the components of that vector by some scalar, some number, which we'll call a, then the result is that the vector itself gets multiplied by that number a, okay? And notice over here, I don't have any lines around the v or the a. So over here, I'm not talking about the magnitude of v. I'm talking about the vector v itself would get multiplied by the number a if we multiply both of the components by a. And the converse of that statement is true also, which is to say that it's also true the other way around. If we have some vector v and we multiply that vector by some number a, and then we ask ourselves, what would be the components of the new vector that we get? The components of the new vector would just be a times the components of the original vector, ax and ay. So now let's go back to the original rule that we said, which is very similar to this one, except we're talking about the magnitudes. Okay, so we have these magnitude symbols around everything. We did an example of that over here where our x was -3, our y was 4, our a was -2. But let's go ahead, and we saw that this rule worked in that example, but we don't want to know that it works just in one example. We want to know that it's true no matter what numbers we use. So what we're going to do now is a proof that this rule always works, no matter what we choose for x and y. To do that, we're just going to call the components x and y, and we're not going to use any concrete numbers at all. So if we have some general vector here, v, and the horizontal component is x and the vertical component is y, then the magnitude of that vector would be the square root of x squared plus y squared. Okay, so this is the magnitude of this vector. This tells us how long this vector is. Now, what if we take the components x and y and we multiply them by some number a. Then the new components would be ax and ay, okay? And the vector would look somewhat different from our original vector. Then we can ask ourselves, what would be the magnitude of the new vector? Well, to figure that out, we would just do the square root of ax squared plus ay squared. All right, now let's simplify things here a little bit. Ax squared is the same thing as a squared times x squared, okay? Which hopefully you remember from learning your laws of exponents. If we have a product which we're raising to some power, then we get the product of the powers. Okay, plus this would be equal to a squared y squared. Okay, now notice that both of these have a squared in them, so we can factor that out. We can rewrite this expression as a squared times x squared plus y squared. All right? If you don't believe that that's true, then you can just distribute. A squared times x squared is a squared x squared. A squared times y squared is a squared y squared. So this is just another way of writing this. Now, when we look at what we have here, we have some number a, and then we're squaring it, and then we're taking the square root of it. What would that give us? It would give us the absolute value of a. All right, so as an example, I know I said I wouldn't use concrete numbers, but I just want to show you why this is the absolute value of a. So as an example, if I were to take 6 and then square it and then take the square root of it, well, 6 squared is 36. The square root of 36 is 6. So this is like my a here is 6, and then when I square it and take the square root of it, I get 6 again, which is the square root of 6. 6 is the square root of 6. So far, so good. What if I had -6 and I wanted to square that and then take the square root of it? -6 times itself, -6 squared is, again, positive 36, and then 36, and then the square root of 36 would be 6. And 6 is the absolute value of -6. So 6 is the absolute value of -6, and 6 is also the absolute value of +6. So the idea that taking a number and then squaring it and taking the square root of it gives us the absolute value, that works whether or not the original number was positive or negative. Okay. So this can be written as the absolute value of a times the square root. We still have all this underneath the radical, right? So we have the absolute value of a times the square root of x squared plus y squared. But wait a minute, the square root of x squared plus y squared is just the magnitude of v. Okay, that's what the magnitude of v is, square root of x squared plus y squared. So we can rewrite this as just the magnitude of v. So now we have that the magnitude of this vector is equal to the absolute value of a times the magnitude of vector v. So that's where this rule comes from. We just showed that the magnitude of the vector with components ax and ay is equal to the absolute value of a times the magnitude of the original vector v. Okay, something else which I'll point out quickly, which you probably noticed, is that we're using the same symbols here for absolute value as we use the same symbols for absolute value that we do for magnitude. That's not a coincidence. An absolute value is just a magnitude. So if you go back to when you first learned about absolute value, maybe you heard that the absolute value is the distance from 0. So for example, the absolute value to find the absolute value of -5, oops, that's not how you write it. To find the absolute value of -5, we would just ask ourselves, how far away is -5 from 0? And of course, it's 5 spaces away, so we would say the absolute value of -5 is 5. And then what's the absolute value, let's say, of +5? The absolute value of +5, we're asking ourselves, how far away from 0 is 5? Well, 5 is 5 spaces away from 0, so the absolute value of +5 is also 5. Okay, but that's exactly the same question as if we had drawn an imaginary vector over here and then asked ourselves, how long is this vector? It's 5 units long. And if we had drawn a vector over here and asked ourselves, how long is this vector? In other words, what's the magnitude of this vector? It would also be 5. So an absolute value is just is really the same thing as a magnitude, except that you usually use the words absolute value when you're talking about just a regular number, and you use the word magnitude when you're talking about a vector, which is in 2 dimensions, got some directions pointing somewhere, but really it is the same thing. All right, so let's move on now. Okay, so we can find a unit vector. A unit vector is just a vector that has a magnitude of 1. So keep that in mind. A unit vector is a vector that has a magnitude of 1, which is why we're using the word unit, as in 1 unit. We can find a unit vector which is moving in the same direction as vector v by multiplying the components of vector v by 1 over the magnitude of v. So let's see an example of that. There it is. I was worried for a second that I forgot to draw it, but there it is. Okay, so again, let's take our the same vector that we used in the first example, vector f, and let's say that our goal was to figure out the components of a vector that is moving in the same direction as f, but only has a magnitude of 1. Well, we saw earlier that the magnitude of vector f is 5. We did that before, if you remember, up here we said that the magnitude of vector f was 5. So I'm not going to do all of that again. But we can use this rule over here, and we could just multiply the components of this vector by 1 over 5. Okay, so in other words, if this component was -3, and we multiply that by 1 over the magnitude of vector f, which is 5, so 1 over 5, then we would get -3/5, which you can see that I wrote over here. And if we multiply this component by 1 over 5, again, 5 being the magnitude of vector f, then we would get 4 over 5, okay? And that's what I wrote over here. And these are 2 ways of writing this vector over here. We could call it -3/5 I plus 4/5 j, or we could just use the angle bracket notation and call it -3/5 4/5, okay? But now let's go ahead and just verify that this vector does, in fact, have a magnitude of 1. How can we verify that? Well, we can do the square root of -3/5 squared plus 4/5 squared. All right, and then -3/5 squared means -3/5 times -3/5, which would be +9 over 25, plus 4/5 squared would be 16 over 25. We can factor out this 1 over 25 here and say that this is equal to 1 over 25 times 9 plus 16. You'll notice that this is very similar to what we were doing in the last proof. And then the square root of 1 over 25 is actually 1/5. If you do 1/5 times 1/5, that gives you 1 over 25. So this is the square root of this. We can pull that outside of the radical. And then we have the square root of 9 plus 16, which is 25. All right, and then, so the square root of 25 is 5. So this is equal to 1/5 times 5. And 1/5 times 5 is just 1. Okay, so we just verified that this vector does, in fact, have a magnitude of 1. All right, and you can see that this is very similar from the proof that we did earlier. But I am just going to go ahead and prove this very quickly. And here's the proof. We don't need to do a lot of work here. You just saw an example of this in action. So here's the proof of this rule. Recall that if vector v has components x and y, then the magnitude of the vector ax, ay would be equal to the absolute value of a times the magnitude of v. That's the first rule that we talked about in this video. So if we use 1 over the magnitude of vector v, if we let this be our a, then we can replace all of these a's in this rule over here with 1 over the magnitude of v. So you can see that what I wrote over here is exactly what I wrote over here, but instead of a, I wrote 1 over the magnitude of v. So if we choose to multiply the components of this vector by 1 over the magnitude of v, then the magnitude of the new vector would be the absolute value of 1 over the magnitude of v times the magnitude of v. But the magnitude of v is just a positive number. So the absolute value of this would just be 1 over the magnitude of v. Okay, and then we're still multiplying it by the magnitude of v. And then these cancel over here, and we get 1. Okay, no matter what the magnitude of v was, if we multiply the components of v by 1 over that magnitude, then the magnitude of the resulting vector would be 1. And we just saw an example of that over here. Okay, and you can see that what we wrote over here is very similar to what you saw in that proof just now. Okay, so I think I'm going to end the video there, and have a great day.